So, good day again, students, and welcome to this lecture in which we shall have a look at the different processes that are used to use the energy that is latent in the biomass. And also we will have a look at the processes used to convert solid biomass or liquid biomass into upgraded fuels. However, we will concentrate only on such technologies that are commercially available today, and we will not really go into any details about the conversion processes. Before we go into the course literature, let's first introduce some fundamental concepts about the different processes that are at hand. And the first and most important thing to understand is that any fuel-fed process involved in the energy supply system has the ultimate aim to make practical use of all the chemical energy latent in the fuel. Now, making use of all the chemical energy is achieved by one and only one process, and that is a complete oxidation. And this complete oxidation is similar basically to the reverse photosynthesis reaction, as we've talked about before. Now, there are two elements that are essential for this, and these are carbon and hydrogen as present in the fuel. Looking at very simplified chemical reactions for this, we can see that to oxidize one carbon atom into carbon dioxide requires one molecule of oxygen, which is denoted O sub 2, according to this simple reaction that solid carbon reacts with gaseous oxygen to form gaseous carbon dioxide, and energy is released. Similarly, we can set up a simplified chemical reaction, oxidation reaction, for hydrogen. But in this case, we need two hydrogen atoms and only 1/2 oxygen molecule to form one molecule of water vapor. And again, energy is released. So to summarize, we can say that there are two major energy-releasing reactions, and these are the oxidation of carbon to carbon dioxide and the oxidation of hydrogen to water vapor. From these reactions, you will realize that there is a constant and fixed ratio between the number of carbon atoms and the need of oxygen molecules, and there is a constant and fixed ratio between the number of hydrogen atoms and oxygen molecules. That means that if we know the exact composition of the fuel, then we can calculate exactly how much oxygen is needed to do a complete oxidation, and hence to release all the energy. So let's assume a model fuel, and we assume 240 grams of this model fuel, dry substance containing 120 grams of carbon, that's 50% of the dry mass, 17 grams of hydrogen, 96 grams of oxygen, and 7 grams of ash. That corresponds to an analysis of 51.5% carbon in the dry ash-free substance, a little more than 7% hydrogen in the dry ash-free substance, and a little bit more than 41% of oxygen in the dry ash-free substance. The ash content is just below 3% of the total dry substance. You may want to refer back to the appendix about fuel analysis to remember the terminology in fuel analysis. Let's add to these 240 grams of dry fuel another 108 grams of water, and that makes up 348 grams of moist fuel with a water content which is 31%. This is a perfectly normal solid biomass. It could be basically woody or it could be herbaceous. The analysis is quite normal for a biomass. But now we also assume that the net heating value for the dry ash-free substance is 20.5 megajoules per kilo. And using the ash content and the water content, we can then calculate the net heating value for the real wet fuel to 13.0 megajoules per kilo. Later on we will go through how the heating value is treated in detail. We've already mentioned it in a previous lecture, but we will go through it in some more detail. It's covered in text section 4.1. Now we have this model fuel, and let's then see what happens in case we want to combust that fuel. We know that one carbon atom for complete oxidation requires exactly one molecule of oxygen. And we can use that to calculate that 120 grams of carbon will require exactly 320 grams of oxygen. And similarly, we can calculate that a complete oxidation of the 17 grams of hydrogen that we had in the model fuel will require 136 grams of oxygen. And then the fuel already contained 96 grams of oxygen. Hence, we only need to add 360 grams of oxygen via the combustion air to arrive at a complete combustion. But then we have to remember that air is, and I use very round numbers here, air is about 80% by volume of nitrogen and only about 20% oxygen. To add 360 grams of oxygen, we have to add also a lot of nitrogen, and that amounts to 1.26 kilos of nitrogen that has to be added. So we have, from the beginning, 348 grams of fuel. We have to add 1,620 grams of air to oxidize it, and the gas we finally get then becomes 1,961 grams. Almost 2 kilos of gas is what we get. And that gas is composed of 440 grams of carbon dioxide, and that comes from the combustion of carbon, which was 120 grams of carbon plus a total of 320 grams of oxygen. We get 153 grams of water vapor from the combustion of 17 grams of hydrogen plus 136 grams of oxygen. And then we also had the water in the fuel, which was 108 grams. That was the fuel moisture. So the total water vapor in the final gas is 261 grams. And then, of course, the gas we finally get, the flue gas, will also contain all the nitrogen, which is 1.26 kilos. So this makes up for almost 2 kilos of flue gases from 0.35 kilos of fuel. The total mass balance, as shown in this slide, always have to be fulfilled, so that all the mass that we input into the reactor has to come out of the reactor. So it's always a good thing when you want to do this type of calculations to add up all the input and all the output and check that it fits. And as you will see from this slide, it fits in this case. But there is not only a mass balance to be fulfilled, there is also an energy balance to be fulfilled. The total input in this case was 0.348 kilos of fuel, and that fuel had a heating value of 13.0 megajoules per kilo. To release that energy, we had to add 1.62 kilos of air, and that gave us finally 1.96 kilos of gases. The total energy released is 0.348 kilos of fuel multiplied with a heating value 13.0 megajoules per kilo, and that is about equal to 4.5 megajoules. All this energy is now present in the gas and is represented in the gas by an elevated temperature. So the gas from direct combustion becomes hot. And in this case, the gas temperature will be just about 1300 degrees C. This is what we can achieve from that fuel when combustion air is fed in at ambient temperature. If we preheat the air, we can arrive at a higher temperature. But for reference, remember this temperature, 1295 degrees C. Now it's quite common that people want to gasify fuel, and we'll talk a little bit about gasification. We use the same model fuel as an example. Now, gasification is a transformation operation. The aim of gasification is not to release the energy from the solid fuel. The aim of gasification is to retain all the energy from the solid fuel in the product gas formed during the gasification process. But the gasification process needs to be run at an elevated temperature. And to arrive at that elevated temperature, we have two options. Option one is to add commercial external energy to the gasifier, for example by electrical heating elements. Now that would be very expensive, so that is not the method used. Instead, what we do is that we add a little bit of air so as to combust a part of the fuel, and by that combustion release sufficient energy to arrive at the desired process temperature. And if we assume that the desired temperature is 700 degrees, then we will only have to add less than 300 grams of oxygen to arrive at that temperature. And that is then, in this case, where we had more than 30% moist fuel. If the fuel is drier, we have to add only less oxygen. So the drier the fuel, the less oxygen we have to add to arrive at the desired process temperature for gasification. In this case, assumed at 700 degrees, which is, within parentheses, a very low gasification temperature. More typical gasification temperatures are about 850 to 900 degrees. But in this case, for this model fuel, we only have to add a bit less than 300 grams of oxygen, about 280 grams of oxygen, to arrive at the desired process temperature 700 degrees. The gas we finally get will then contain all the energy from the original fuel. That was about 4.5 megajoules. But that energy will be split approximately with this fuel and 700 degrees, 50-50, in sensible energy as represented by the gas temperature, 700 degrees, and in chemically bound energy in gas components. These gas components are mainly carbon monoxide hydrogen and methane and some other hydrocarbons. So remember, the energy in the gas is split in two parts. Its sensible energy, represented by the gas temperature, and its chemically bound energy. As long as that product gas is maintained at the process temperature, 700 degrees, then all the energy from the original feed is still there. But if the gas is cooled down, then we lose the sensible energy, unless, of course, we recover it in one way or the other. But if the gas is cooled down, we lose from the gas the sensible energy. And if we cool down the gas to ambient temperature, then we have lost 50% of the energy content in the product gas. And only those 50% of the energy content that are there because of chemically active compounds, carbon monoxide, hydrogen gas and methane gas, only that energy remains. So to keep all the energy and keep a good energy balance of the gasification process, we need to retain the gas at the highest possible temperature, unless we want to introduce an expensive and complicated heat recovery process. Looking then at the gas quality, you will realize that this gas still contains all the fuel moisture that was present in the original solid fuel. Certainly, that moisture is now in the form of water vapor, but it is still there. And that water vapor is a thermal ballast to the gas. So is also the nitrogen from the air that we added, the gasification air that we added to get in the about 280 grams of oxygen. And there is more ballast. Parts of the ash, like some corrosive compounds of chlorine and sulfur, and the volatile metals like zinc and sodium, and alkali sulfides and so on, will also be present in the gas. So this gas is not all free from ash components, and the gas still contains all the water that was present in the original fuel. If you want to get rid of these contaminants, and if you want to get rid of the ballast without losing energy, then you will have to take these contaminants and the ballast gases out of the gas at 700 degrees. Assume we keep the gas at 700 degrees. To finally release the energy from the product gas, you will have to add the remaining oxygen. And if we assumed that we had to add 280 grams of oxygen for the gasification process, then we will obviously have to add the remaining 80 grams of oxygen to combust the gas and finally release the energy. With that oxygen comes more nitrogen, if we use air for combustion, of course. And finally, after we have combusted the gasification gas, we arrive at exactly the same gas as we got from the direct combustion. 1.96 kilos of gas at a temperature 1295 degrees, if we have lost no energy. So basically the gasification with the subsequent immediate combustion is just equal to direct combustion. There is no difference. You do not upgrade the fuel. You do not change the composition of the fuel. You do not alter the temperature that you arrive at. You do not alter the amount of flue gases. So unless you have lost energy on the way, then the final product and the final temperature after gasification with direct combustion is the same as for direct combustion of the fuel itself. In the example we just discussed, the gasification was done using common air as the gasification medium. And then we found that gasification is really only a delayed combustion and nothing else. However, in some cases you really want to use gasification to upgrade the fuel. Now to do that, and that is not covered in any detail in the course literature, but it is mentioned, you would not use common air as the gasification medium. You might even revert to, in the most advanced cases, a pressurized gasification process using pure oxygen and water vapor as the gasification media. Doing that, the gas quality, the product gas quality, may even be synthesis gas, which is mainly composed of carbon monoxide and hydrogen with only very small amounts of methane in it. And that synthesis gas can be used for chemical synthesis into dimethyl ether. It can be purified into hydrogen. It can be turned into methane. You can do a lot of different things with it. But then we are talking a very advanced gasification process. Generally, however, if you really want to have an upgrading of the fuel, the thing is that you want to get rid of the contaminants and of the ballast that was present in the original solid fuel. And to do that, either you can do it at a high temperature, at the process temperature, and that way it will not cost you any energy. Or you can cool down the gas and do the cleaning at ambient temperature. Now the problem with these is, with the first case, hot gas cleaning, no such technology is readily available for that today. With the second technology, cleaning up the gas at ambient temperature, this requires a complicated energy recovery, and then you will have a cost associated with it. So gasification is one example of a thermochemical conversion, and there are basically three different types of thermochemical conversion processes that can be used. It's liquefaction, in which you at elevated pressure add hydrogen and carbon monoxide to the fuel at elevated pressure and temperature, I should say, to produce a liquid, an oil, from the fuel. It's gasification that we just talked about, and in this illustration it's an advanced gasification where you use water vapor and oxygen as the gasifier media. You also need an elevated temperature. It's pyrolysis. In pyrolysis, the only thing you do is you heat up the fuel. It's a dry distillation, and the pyrolysis process produces three different types of products. It can be a liquid pyrolysis oil or tar. You can get a solid fuel, that is charcoal, and you can also get a gaseous fuel, that is a pyrolysis gas. The proportions between these can be set by the process temperature, by the process pressure, the heating rate, etc. But to make things very simple, we shall only distinguish between high temperature pyrolysis or charcoal production and low temperature pyrolysis or torrefaction. Torrefaction is an incomplete low-temperature pyrolysis, typically running at about 350 degrees C. And that produces a tar-containing char. Now, the fact that the char contains tar means that it gets some partly hygroscopic qualities. So that char is brittle, it is easy to grind, it has a high heating value, around 30 to 35 megajoules per kilo, and it is to some extent hygroscopic, so it can take a moist environment without being destroyed. Torrefaction has become a modern technology, and it's not commercial yet, but it's one way to turn wood and also to some extent herbaceous biomass into what is commonly called green coal. A fuel that is black, of course, that has a heating value resembling that of coal, and that is easy to grind and could easily be used in co-firing applications. To summarize the thermochemical conversion processes, we can say that basically we have three different thermochemical conversion processes. It's liquefaction, pyrolysis, and gasification. But all three have a number of things in common. One is that the energy in the feed shall be retained for a later combustion of the product fuel. So it is essential that the energy input to the processes and the energy losses from the processes are not too big. The product fuel requires an upgrading. That is, it requires that you take away the contaminants and the ballast that was originally found in the feedstock if you really want to arrive at a fuel upgrade. All three routes have in common that if they are to be autothermal, then the feedstock may not be too wet. In the example we discussed previously, we had a fuel that had 31% moisture, and we had to add almost 300 grams of oxygen to that fuel to gasify it at 700 degrees. If the moisture content had instead been about 10%, we would only have had to add around 1 or less than 100 grams of oxygen. And in that case, what would happen is that very much more of the chemical energy in the original feedstock would have been retained into the gas. So the drier the fuel, the better the energy economy. So usually, thermochemical conversion requires a drying of the feedstock before the process. All three routes have in common that there is a process cost, not only for operation, but also for capital, because you have to do an investment in the thermochemical conversion plant. They also have in common that you will lose energy, and hence you will lose efficiency when you do a conversion. So these are the four major drawbacks which are common to all thermochemical conversion processes. However, in some cases, the final process may demand a fuel in a specific state of aggregation. For example, if you want to run a gas turbine, you cannot use a solid fuel. So if you want to run a gas turbine, then using basically wood chips as the feed, then you simply have to convert the wood chips into something else. You have to convert the wood chips into something that is suitable for a gas turbine, either a gas or a light liquid. Sometimes the final process may gain efficiency. It may gain so much efficiency as to pay for the losses that are caused in the conversion process. Sometimes the final customer may be willing to pay the extra cost. Ethanol for cars, for example, or biomethane for cars, or dimethyl ether for cars. Maybe the driver is willing to pay the cost for the conversion, and in that case, well, if you actually remove corrosive component and erosive ash from the product fuel so that the fuel really becomes pure and clean. Going back to the gas turbine example, if you use wood chips for gas turbine firing, then the gas turbine blades will rapidly be eroded and corroded by the solid particles that are found in the flue gases from wood chips combustion. But if you gasify the wood chips and you then remove all the erosive and all the corrosive components from the gas and you feed the gas turbine with that gas, then you can run the turbine, the gas turbine. So there are not only drawbacks with the thermochemical conversion, but there are also positive sides. But there has to be a balance between the cost and the gain of the conversion process, and that has to be evaluated over the whole process chain up until the very last process step. Sometimes thermochemical conversion is an excellent idea, but in very many cases it is not. So remember to exercise your critical mind and to trust the conclusion that you arrive at when you exercise your critical mind to the conversion processes. There is an oversell of thermochemical conversion presently, and thermochemical conversion is not the solution to everything. Sometimes, yes, in very many cases, direct combustion is preferable. We just discussed the thermochemical conversion processes, and we found that there were some drawbacks and some advantages with them. And let's now go into the biochemical conversion processes. There are basically two of these. It's anaerobic digestion, where the process runs without access to oxygen, so it's an air-sealed process, and it's fermentation, in which oxygen is present. Now, both of these are biochemical conversion processes. They are operated by microorganisms. And then you have to remember that microorganisms, they thrive in water. As a consequence of that, the feedstock can well be a sludge with 95% water in it and only 5% solids. It's wet enough, basically, to be used as a fire extinguisher, but such biomass can actually be used in biochemical conversion. It cannot be used for energy purposes in any other way than via biochemical conversion, and hence the biochemical conversion processes are necessary parts in the sustainable bioenergy system, because without them a huge energy resource, all those dripping wet materials, would not be utilized at all. Now, since the biochemical conversion processes then make use of sludge that has a negative heating value that could be used as a fire extinguisher, and creates a combustible fuel out of that. Both of these processes are in themselves upgrading processes, transforming a non-useful and non-combustible resource into a combustible fuel already in the first step. And then that combustible fuel can then be further upgraded up to vehicle fuel quality, which is more than 95% methane, or basically more than 95% ethanol, using only fully commercial and mature technologies. You can also use the primary product fuel directly. Just remember, there will be corrosive components in it. So you may want to look at the materials used in your fuel handling system. Otherwise, your fuel handling system may be corroded away and its lifetime may be shortened significantly. Now, the final conversion process that is mentioned in the course literature is the pure chemical conversion, which is esterification of fatty acids. The product of that is called FAME and is commonly used as a diesel additive, like rape methyl ester and alike. The raw material for these processes can be extracted bio-oils or oil residuals from food processing, or it could be frying oils from restaurants and kitchens. The problem with using these extracted bio-oils already from the beginning, or cold-pressed oils already from the beginning, is storage. As was mentioned in the lecture about storage, these oils are composed of a mixture of different oils and different hydrocarbons, some of which will oxidize already at room temperature, some of which may solidify. And the idea with esterification is, one, to homogenize the material, and two, to make it more stable so that it can be stored. So these oils can be used directly, but using the esterification process, which basically means that the oil is treated together with alcohol to form an ester, means that its storage properties are improved radically. The product fuel, fatty acid methyl ester, or FAME, may replace light fuel oil in basically any industrial fuel oil application. But just remember that if the product fuel is not purified and cleaned, then it may still contain some corrosive components. So you may want to look at the choice of materials in pumps, filters and packings for use as a diesel oil substitute or additive. Then you cannot demand of the car owner to change the material in their car engine. So for that application, the corrosive components have to be removed before you sell the final product fuel. So what we've done now is that we have identified basically three different thermochemical conversion processes, namely gasification, liquefaction, and pyrolysis. And we have identified two different biochemical conversion processes, namely anaerobic digestion and fermentation. And then we have identified one pure, quote-unquote, chemical conversion process, namely esterification of fatty acids. These different processes have different roles to play, and they produce different types of fuels. So biomass can be converted into a liquid fuel, into a gaseous fuel, or into a solid fuel with a different quality than it had from the beginning. Biomass can be upgraded via conversion, but the conversion can also only be a conversion without any upgrading at all. and you need to judge whether or not to use an upgrading process instead of combustion. You will never, even if you use upgrading, you will never get rid of the combustion process. It's always the final process to actually release and make good use of the energy in the fuel. So we have now summarized all the processes that are available in a few groups. And going into chapter 0400 and looking at the content of the chapter in the left-hand side column, you will notice that the chapter is split into basically 4 different parts. The first part is a general introduction to the different processes: torrefaction, pyrolysis, liquefaction, gasification, fermentation, transesterification, and digestion. Then followed by a general discussion of the heating value. So the first section of this chapter is basically introductory descriptions of the different processes. This is followed by a section where the different states of aggregations are treated, like how solid biomass can be turned into a solid biofuel and the energy extracted, or a solid biomass can be turned into a liquid biofuel and energy extracted. Solid biomass into gaseous biofuel is treated in the next section. Liquid into liquid, sludge into liquid, and sludge into gaseous biofuel is treated in the next section. After that, we bring up different applications to discussion. And the first ones and the most important ones are the ones using direct combustion. And then different scales are discussed, all from small scale systems that are for the individual house and extending up to large district heating systems with combined heat and power production. Finally, different specialities are treated, like different options with large-scale district heating and combined heat and power production, such as the production of district cooling or co-firing with coal. Finally, special processes that really demand fuel conversion are treated, such as the production of transport fuels or the operation of fuel cells. And there's also a short section about emissions and flue gases. You will be able to find this described in different ways in different textbooks, like for example in the book by Ralph Sims, The Brilliance of Bioenergy in Business and in Practice, which was printed in 2002. On page 11 you will find this diagram where you will recognize the different terms that we have introduced previously. You will recognize the raw materials at the bottom, and then you will recognize the direct combustion as one major way to go. You will recognize 2 of the thermochemical conversion routes, that is gasification and pyrolysis, though liquefaction is not specifically mentioned in this book. You will also recognize the 2 biochemical conversion routes, anaerobic digestion and fermentation. And finally, you will recognize the esterification route, the chemical conversion route. So this diagram describes exactly what was introduced previously and also what is discussed in chapter 0400. So it really adds nothing, but if you want to have a parallel description, you can go into Sims' book or a number of other textbooks that are for sale since the last roughly 10 years. The specific chapters on process properties of lignocellulose, of herbaceous biomass, putrescibles, and general residuals and waste, will bring up the specific processes that are best suited for these different biomasses. So we will not go into these chapters now, but you will have to study these chapters yourself. So that was basically the introduction to the processes and to the available technologies to produce and extract the energy from the biomass and from the biofuel.